chapter 7 is the chapter where you will finally find the solution for the question that we started with the class. Remember I told you when I was undergrad and I went after the class to my professor and asked him why that the vision nozzle dropped the density so much to the extent that the increase in the area is not good enough, that the flow will actually need to accelerate to compensate for it and become supersonic. And he said, go to grad school. Today you go to grad school. Today you will find out why does the diversion nozzle accelerate the flow. Right? Yes. So this is not just for diversion nozzle. It's also, you know, in chapter 8, I will give you, and in the midterm, I will give you an airfoil. Every time I'll give you airfoil and basically ask you to calculate the lift and the drag on the airfoil. And almost always, the students don't recognize what should they draw here at those noses. They know how to solve an oblique shock wave, that's not a problem. And they know how to solve the other thing. It's called expansion fan. That's what we're going to study in chapter 7. But they don't know how to mix and match, or how to decide which one is going to start. Right? So basically, here, and here, what will happen at those places? Right? So to start, you need to be able to say the difference. But right? This is completely different. This, the flow when you hit him with a nose like this, definitely an oblique shock wave. If you cannot see this is a problem. Right? If you cannot see what? If you cannot see that this is different than this, right? So this will not be an oblique shock wave. Why? We are giving him more area, right? Amazingly, that's the mistake that they make in the midterm. They come here and they say oblique shock wave. All right? So, for example, what will happen at the front? Oblique shock wave. What happened at the bottom?
Chapter 7.
No, oblique shock wave. At the bottom, oblique shock wave. What happened here? I'm talking about this point.
That's chapter 7.
Excellent. That's when they make the mistake, right? They actually usually would say on oblique shock wave. But it's an expansion fan. And the reason why it's expansion fan, again, is because you realize the flow was going like this, and suddenly he's going like, wow, look at all this area. Right? That was basically what happened. Yeah, yippee. It's like my kids, whenever we go downhill, they were like, wow. They have very good acceleration sensor in them. They can tell, basically, that we're going down the hill. So anyway, so first let's assume it's an oblique shock wave, and I will prove you that it's wrong. It will never be an oblique shock wave. All right? So that's the reason why it's wrong. Let's assume that when we give him something like this, there will be an oblique shock, not oblique shock wave, but an oblique something. Something that will change the flow direction over that line. So what happened? Before, it was horizontal, V1. After that line, what will happen? It should go with the new wall, right? So V2, that direction, is the direction of V2. We are not really sure how far will it go, like how large V2 is or how small, but that's the direction of V2. Okay? So how we calculate, if we want to calculate the velocity, what do we do? From, you know, a new chapter, I'm asking you to calculate the velocity. Where do you go?
I'm guessing we're going to E now.
But before we generate, I'm asking you to generate that appendix, right? And it's going to be appendix E. Robert is right. But how we generate those appendix? We do what?
Formulas.
How do we come up with the formula? How do we drive the formula?
Your momentum equations.
Excellent. That's what I wanted to hear. When someone asks you about the velocity, you go after the momentum equations. That's where the velocity are. That's, if you solve the momentum equation, you get your momentum. That's what we did in chapter 3 and 4 and 6 and 7, and we'll do it in 9 and 10. So here's the momentum equation. You realize there are two momentum equations, horizontal and vertical, or tangential and normal. Any way you split it. So if you write it in the tangential direction to this thing, you will find that there is no pressure. I'm assuming we're going to have like a very small, very thin control volume. So in the tangential direction, there is no pressure. And so the momentum equation will boil down to just like the tangential equation in the oblique shock wave chapter. it was like this, V1t equal V2t. Remember in the oblique shock we said V1t is the same as V2t? M1t was different from M2t. The tangential Mach number was different because the temperature is different. But the velocity was the same, before and after. So for the same reason, the momentum equation here will result in V1t equal V2t. So that's good news. That basically say that if you had your hand on V1 tangential, that's exactly V2 tangential. So now V2 normal is normal to this line, is normal to V2 tangential. So all you have to do is just make a line like this, and it should be a line. Imagine it's a line. That line intersect with the direction of the new wall, and this point, that's the end. This must be V2. So the geometry basically tell you that V2 magnitude should be bigger than V1. And not just that, V2 normal from the geometry need to be bigger than V1 normal. Just from the geometry. If it's happening over one line, which will prove that's impossible, but if it happened over a straight line, V2 normal will be bigger than V1 normal. And if you remember when we were solving an oblique shock wave, we had two solutions, two mathematical solutions. One of them increased the entropy, the other one decreased the entropy. One of them we rejected because the entropy cannot decrease in an adiabatic flow. So for the same reason, if you make V2n bigger than V1n, that will basically make the entropy negative. So it cannot happen in an adiabatic flow. The entropy cannot decrease. Therefore, this is impossible to happen based on the second law. All right? Also, physically, how we can arrange those, how we make this oblique shock wave. It's probably, if you zoom in at that corner that generates an oblique shock wave, I'm zooming in. That corner, you think it's like tuck, tuck, 30 degree, but in real life, it's like tuck, 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 tuck. Right? I mean, it's, no matter how nice this angle is, it's probably on a smaller scale, it's like something like this. So each one of those guys will generate Mach wave, Mach wave, Mach wave. I'm talking about the fillet in the nose. So all those basically shock wave, Mach wave. Each one of them have mu1, mu2, mu3. Each mu is bigger than the one before it. Why? That's one reason. So Sean is saying because the wall is bigger, but I'm not talking about the wall. I'm talking also about the mu itself. The Mach number, excellent. The Mach number, because he's decreasing, the mu get bigger. This is the same answer. He gave it twice today, John, basically. Right? The first one was for the oblique shock, why the Mach number is he get weaker, why the theta will get bigger. The same reason for the mu. Right? So mu is getting bigger, and according to Shen, also the wall is getting closer. So what I'm trying to say is that those guys will have to meet, will have to collapse, will have to combine and form one oblique shock wave. But the opposite will not happen. If this was basically the corner was like this, the mu is actually getting, as the flow is accelerating, that mu is getting smaller. So the mu is getting smaller, the wall is getting far away, those guys will never meet. So as a result, all those Mach waves remain Mach waves. So basically what will happen at the corner here is bunch of Mach waves that will never meet. That's really nice. Because we know a Mach wave is isentropic. And they remain isentropic. Right? So this is isentropic expansion fan. Right? This is isentropic expansion fan. So this will actually, this fan will open like this and it will remain isentropic. This is excellent news because isentropic mean P naught is the same as P naught. Of course T naught is the same as T naught. That was even for an oblique shock that we had that. But the point is if you have P naught here, it's the same like P naught here. Alright? And the flow will gradually change direction from M1 to M2. From the horizontal to the new wall direction. Right? And so the typical problem would be you have the stuff before, we want the stuff after, and I'm telling you we are turning at 10 degree, for example, or 5 degree, or whatever. So the hard part is getting the Mach number, but let me assume we have the Mach number. I'll show it to you next slide. But let's assume we have the Mach number. Can you get the pressure and the temperature? Yeah, because P02 is the same as P01. So whatever the P0 here is the same here. And so if you have M2 and P02, how you get P2 out of them? No, no. If you have M2, that's the Mach number already after the shock. If you have M2 and P02, how you get P2 out of it? Huh? Excellent. We are back again to chapter 3. Right. So it's we will basically use chapter 3 to calculate the pressure and the temperature after the shock. If we know the Mach number after the, not the shock, sorry, the fan. If we know the Mach number after the fan, after the expansion fan, we will get the pressure and temperature from appendix P, just like isentropic flow. The question is how we can get the Mach number after the fan. Right? This is, by the way, so rather than saying it's the same P0 and let's go to appendix P, he basically wrote P2 over P0 and P1 over P0. This is basically the appendix P equation, but he wrote it twice. And then he called this a new equation now for P2 over P1. Why is that useful? So this is in chapter 7. This equation is chapter 7 and it's on page, can anyone help? 237. All right. So why he's doing this? Because in case you already have P1, not P01, P1, and all you need is P2. Huh? And you don't want to go and get P01 and then go to appendix P and get what's P2 and P02 and M2. This equation will basically tell you if you have P1 and M1 and M2, you can get P2 immediately, rather than going to appendix P twice. Right? Imagine if you have M1 and P1, what you will do? You will have to go to appendix P to calculate P01. And then, well, you say P01 is the same as P02. And then you say, well, P02 and M2, I can calculate P2. And that's how you do it. But this equation allows you to immediately jump from P1 and M1 to get P2. Does this make sense? And the same story for T2 and T1. You can go to appendix P twice to calculate your T01 and say it's the same as T02, or you can basically just use this formula. Let me clean the P0, they are the same. This formula will immediately tell you if you have T1, M1, and M2, you can calculate your T2. And it's on the same page, right? 237?
Yeah.
Okay, so a lot of students really like this more than let's go to appendix P and calculate P0, and it makes sense, right? So here is the calculating the Mach number after the turning. All right? So he will do it for a very small change, and then he will integrate for a big change. So he will do it for like really, really tiny change, not even 1 degree, just a very small time turning. And then he will be able to integrate this equation to say for 10 degree turning, how much increase in Mach number I will get. Obviously the Mach number will increase. When you give him more space, the Mach number will increase. So basically, I will not write the equation for you, but if they follow from the continuity and momentum and energy equation, basically, or especially continuity and momentum. So if you write them, you will end up with this. This is a relation between V and the turning. The turning is d nu. Okay? The turning is d nu. This is important.
That's
Nu. Okay, that's the turning. So here he want a relation between the Mach number and the turning. So he want to get out the V in terms of the M. Well, here is what this equation will help. And so once he change the V to M, he will have this. This is an integration basically between the M and the turning, d nu. He integrate from, look at this. So M1 corresponding to nu1 and M2 corresponding to nu2. Right? So if you ask me what is nu1, can you show me where is nu1? I can't. I can't. There is no new one in this drawing. Right? But nu 1 is the angle associated with M1, and nu 2 is the angle associated with, and the difference between them is the turning. Alright? So he basically, to be able to use this in all the problem, he said, well, let's just have reference angle with reference Mach number. The reference Mach number is 1. And so after he integrated, he substituted basically between 1 and M, and he started basically this big appendix. So now appendix E will list the Mach number and the nu. Let's talk about the mu in a second. But there is M and the nu. Alright? What is the nu? I cannot tell you what's the nu, but I can tell you that the turning that's then degree is the difference between nu 1 and nu 2. Alright? And as a matter of fact, this equation, that the turning is nu 2 minus nu 1, this is a must have equation in every single problem that will have expansion fan. So if you see any expansion fan, before you even think, write this equation. You will have to use it. There is no way you will not use it. Alright? And actually all the problem being, you have to solve the problem with this equation. Okay? How is that possible? Well, this equation has 3 terms, the turning, nu 2 and nu 1. You should think about this nu 1 and nu 2 as also as if there's M1 and M2 written here. What's the M1 and how you can get it? Appendix E. There is a link between the angle and the Mach number, the angle and the Mach number. It's this table. Can you open Appendix E for me for a second? Page 646. How many columns you have? Not just M and nu. There is also mu. There is also mu. Well, what is mu? It's sine minus 1. 1 over m. He really didn't have to do that, you know, but he's so nice. So he just also throw in another mu for us. But you know what's the mu? You can generate mu. You don't need the table for it. Sine minus 1, 1 over m. Why mu is different, is useful? Well, we'll see it next page. For now, let's ignore it for a second. So that table which lists m and nu, m and nu, m and the angle, will basically allow you to use this equation. How? Let's imagine, here's the problem. M1 is 10, the turning is 10 degrees. He wants the Mach number 2. Alright? So again, I want you to use this equation and think, well, this is linked to M2 and this guy. And this guy is linked to M1. Three unknown or 3 variable in one equation. Obviously, he can give you 2 and ask for the third. That's always the case. Either he will give you M1 and M2 and ask for the turning. He'll tell you how much should we turn it so that the flow will accelerate to 10 degree, to Mach 3. Or he will give you Mach 1 and Mach 2 and tell you, well, how much was the turning that will... So, we have to have 2. We calculate the third. In this case, what do we have? M1 and the turning. And you want the M2. So basically, from M1, you can calculate the angle. The turning is 10. The new one from the chart or from the table at M1 equal to, the value there is 26.27. You put it here. So this is 26.27. And the turning is 10 degree. Can you calculate the nu 2? Of course. The nu 2 would be the 10 plus the 26. So nu 2 is 36. Once you have this as 36, you go to the table and calculate M2. So this one equation, he will give you 2 value in it, and you will calculate the third. And the table is just there to make that conversion between the angle and the Mach number. Is that clear? This, I think, really, this is the easiest chapter ever in the course, right? Especially that once you get the Mach number, you only have 2 equations to calculate the pressure and temperature. No going back to normal shock table, no going to figure D1, you know, it's really easy. And the turning, most of the time, is very easy for you to see. It's, again, the change in direction before and after. So if you know where he was going and now where he's going, how much different did you give him? That's it. All right? Now, sometimes the problem get a little bit difficult when you ask about the fan angle. Why he want the fan angle? Well, maybe the engine, you know, he want to see how large is the engine should be, so that he can finish the engine. So he basically need to know where does the shock finish. Sorry, the expansion fan finish. So sometime, say this is the upper wall, and he don't wanna finish the engine too early before the shock hit the expansion fan. Sorry. So how to calculate this angle, that fan angle? Here is the equation, and it has mu's, right? You don't have to really guess. You can just use the equation, but I would love you to know where it's coming from. So we are calculating this angle. Okay? This angle, that's the fan angle. So this angle is this big angle minus this. Right? Or actually, you know, it can also be this minus this. Right? This minus this. That would be the fan angle. Does this make sense? Maybe if I plot it from here, you will see it. So it's this minus this. What's that? Amazingly, that's mu1. Why? Let me ask you in a second. But believe me, this is mu1 for now. So if this is mu1, what is this? Well, this angle is actually the turning. So we want this guy. Did I say this mu1? I'm sorry. Don't believe me. This is mu1 plus mu2 minus mu1. All right? And the red one is mu2. Very good. So now let's see why this is actually mu1 plus the turning. I mean, obviously, this is the turning. So this suggests that this is mu1. So why this is mu1? Well, if you have a flow like this coming at m1 and you give them any small disturbance, a pin is sitting there, you know, a tiny pin sitting there, what will happen? Not an oblique shock wave. You know, that's a very tiny disturbance. So what will be generated? A Mach wave. If you have a very small disturbance, a piece of paper, you put a piece of paper in the direction of Mach 1, what will happen? Not an oblique shock wave, a Mach wave. I mean, if it's like a big delta, that's an oblique shock wave, but a piece of paper, that will generate a Mach wave. A Mach wave with an angle mu1. And look where I'm measuring mu1. Just like I measured delta and theta and everything. Where do I measure them? Excellent. From the original direction. That was the original direction. And that's why delta was measured like this, from the horizontal. And that's why that's why mu2 was measured from this. Why? Because that's the direction of m2. And you could argue, a very good question right now is, why this is where you measure mu2 from? I'm saying because that's the direction of m2. A good question would be, but you should measure mu2 from the Mach number before the disturbance, not the Mach number after the disturbance, not the exit Mach number. But because this is an expansion fan, because this is isentropic, the last one of those guys is almost like M2 too. I mean, that there's very, very small change before the last one. Right? So what I'm trying to say is the Mach number before the last ray, the last Mach wave, is almost like the Mach number after it. It doesn't change that much.
So mu1 is measured from the horizontal.
Correct. Mu2 is measured from the new wall. Right? And at the end of the day, you're not required to prove this equation. Okay? But I'm just trying to explain to you so that you can come up with your own formula later on, you know, in different courses, in different material. You should be able to generate those equations yourself, not just use it from textbook.
So
Right.
we're adding turning angle.
So the turning angle is the difference between this wall and that wall. And it happened to be also this. This is the turning. Alright? Our book actually have this system that I don't like, which would say, well, this is alpha is 0 here, and alpha is 15 here. What's alpha? That's the direction of the flow. He will have he assign angle for the direction of the flow. Is horizontal, it's 10. If it's going down, it's 15. And therefore, the turning will end up being, he will call it then alpha minus alpha or something. I just think that the turning is very clear to your eye. It's the change in direction. Right? So anyway, so now, by the way, because the flow is isentropic, if I give you M1, I ask for M3, you don't have to solve for M2. You can add them together. Unlike the oblique shock wave, one of you was asking, Amanda actually was asking about this the other day. She was saying, if we have two oblique shock waves, can we just combine them together and get the flow after the third oblique shock waves immediately? I mean, let's feed the solver M1, delta 1, delta 2, delta 3, and tell him, rather than 5, 5, 5, give us the flow after 15 degrees of oblique shock waves. It doesn't work that way. But with an expansion fan, it does. So rather than saying, give me the flow after 5 and then give me the flow after 8, you can immediately tell him, give me the flow after 13. So with that 13, you can get this new angle that corresponds to the new Mach number. All right? Does this make sense? Because it's isentropic. The oblique shock wave was not isentropic. The moment we have been waiting for, the moment we understand why does this guy accelerate the flow. This is the guy who got it when he was a little bit older. But that's his picture when he was a child. Meyer, that's why it's called Meyer-Prandtl-Meyer expansion fan. So Meyer solved this, basically. He solved the flow in the divergent part. And using this Schlieren image, you can see what's going on. So what's going on in the divergent part? Why does the flow, when he hit Mach 1 at the throat, why he goes supersonic in the divergent part?
The turning angle is expansion fan.
Excellent. Because the turning angle away from the wall, that's how you generate expansion fan. Right? And those expansion fan basically gradually accelerate the flow. Right?
Since they're isentropic, you can stick with the end.
It happens slowly, it happens gradually, right? It doesn't happen immediately. So every part you go through the nozzle, it's expanding, right? You got it now? Right. All right. So here's an example. Shock wave, expansion fan, and then shock wave, and first shock wave, and then expansion fan. So you know the drill, right? You know how to solve this. Let me just reiterate one more time how to get, what does he want? He wants the pressure at the end, okay? Required is this pressure, B3. B3 in both scenarios. Do you think they are the same? Expansion and then shock, shock and then expansion. Same angle, 10, then 10, 10. Do you think they will be the same?
Probably have more loss in your shock wave faster.
Say that again.
You probably have more loss in your shock wave with faster loss.
Excellent. John got to the chase. The shock that will have higher Mach number before it, probably this guy, will be more disruptive, will result in lower pressure, right? Lower pressure, or basically lower, it will result in higher draw or higher losses in P naught. And that will make the pressure that you can go up to much lower, right? Not really much lower, it's 99 and 100, but the point is, John was right. This guy, because the Mach number here will be bigger. This Mach number is 3. What do you think the Mach number here will be? Yeah, because the expansion fan, probably, I don't know, 4 something, we'll see it. And so this shock will be stronger. The P naught drop in this shock will be much bigger. And that drop in P naught will result in the pressure, the static pressure, to rise a little bit not much compared to the other one. All right? But first, can anyone help me get the pressure over here, P2? What I just said before, you have to start writing this equation. There is no running away from that equation. And then what? What do we have? We have the turning, 10 degree. We have what else? We have M1, that means we have nu 1. From that you calculate nu 2, and from that you calculate M2. And then what? How can I get my pressure? The equation that gives you P2 over P1, right? Or you can go to appendix P twice if you want. If you have any personal problem with that equation, okay, you can always go to the appendix P twice. But here is the drill. See M1, nu 1, and after that you calculate the turning plus nu 1, that's nu 2. From that you calculate M2, and well, here I'm going to appendix P, but you can just use this equation, all right? You have to go to appendix P not just for that, for M2 get this, but also even for M1. You have to go to appendix P to get what? B naught 1. That's how you can calculate B naught 2, and therefore you can calculate B2. And then the oblique shock wave, I'm not going to go through this. You know how to do it. Right? And this is the second solution, and now let's put them together. 99.4, 100.2. What happened? Exactly what John said, that this shock is stronger. Will waste a little bit more pressure. P naught wise. That's why P3 after it doesn't go up that high. All right? Questions? So, I want to finish with this. We have still 10 minutes, right? 5 minutes? 7 minutes.
You'll get it right in a minute.
All right. So, just like oblique shock wave can be generated by not a physical wall, but actual pressure that push on them, the same thing for an expansion fan. If the flow was leaving here supersonic, let's call it Mach 2. So the Mach number here is 2 already. Why? Because the conversion diversion nozzle. So that Mach exit is 2. And then suddenly the pressure here much lower than B exit. He's leaving at this B exit, the design pressure, and all year long so far we have been saying, you know, if the pressure is lower, things happen outside, that's what will happen outside. So the supersonic flow find that back pressure is lower than him. What happened? He need to go down to that pressure, but because he's supersonic flow, he go by an expansion fan. So an expansion fan will lower his pressure, increase his Mach number, and send him in this direction. That's how he relieve himself. So in order to vent himself or lower his pressure, he need to go away. All right? So the question is, what is this direction that he move in? He's asking about the turning. He's asking, so all those expansion fan problem, he has to ask about M1 or M2 or the turning. That's it. Because that equation is where things are. So this time he's asking about the turning. And the turning is nu 2 minus nu 1. Do I know nu 1? Because I know Mach number 1, right? Do I know, obviously I have to know nu 2 because I need to calculate the turning. So someone need to give me that nu 2. Or someone need to give me M2, because if you give me M2, I can go to appendix E, get, can anyone tell me the M2, what is the Mach number that he will go to, accelerate to? Excellent. You can get the Mach number here, because you know the pressure here, static and stagnation. What's P2? That's the B back. That's the whole point. We expand it so that P2 become B back. And what's P naught 2?
P naught is equal to P naught, or what's in the...
It's equal to B naught, which is equal to BR, because the expansion fan was isotropic. So knowing those two guys, appendix P, you can calculate M2. And from that, you have the angle 2, and therefore you calculate the turning. All right? So here is the solution. Again, this is the equation that we will always use. We have this from the inlet. We have to calculate this. And we will calculate this from B2 and B02. And we are done. Questions for me? All right, thank you.